Okay, in this lecture we'll discuss mostly the processing structure and properties of ceramic materials, because these ceramics are increasingly being used in biomedical applications. Therefore, an in-depth knowledge of the how the ceramics are processed to make different shaped components, or how the properties of ceramics are different from that of metals or polymers, that need to be understood clearly before their biomedical applications can be realized. So, several things that I will be discussing through a series of slides are as follows. First is that structure and bonding, and then structure and bonding, and that basically how the microstructure they look like and what is the typical bonding of the ceramics, that will be discussed. Then it will be discussed about processing of the ceramics, mostly the sintering aspect, because each of the materials, they are essentially fabricated or they are essentially manufactured by different routes. So, for ceramics, the sintering is the most commonly used processing routes, which are largely employed to make different shaped components. Then third one is the ceramic microstructure. So, how the sintered microstructure they look like, how the microstructure is different from that of other materials, that will be stressed upon. One of the major concern of the ceramics is brittleness, and for example, in some of the lectures it has been categorically mentioned, or it has been repeatedly mentioned, that hydroxyapatite, which has been widely regarded as an important bioceramic materials because of their good biocompatibility or bioactivity property, they suffer from extreme brittleness, because hydroxyapatite has a fracture toughness of less than 1 MPa square root meter, so which is around 0.6 MPa square root meter. So, why ceramics are brittle and how the brittleness can be overcome, or how different toughening mechanisms can be invoked in the ceramic materials, that will be discussed. And except the fracture toughness or the toughening behavior, the general mechanical properties of the ceramics like hardness and strength properties, how they are experimentally measured and what are the different formulas typically used to determine the mechanical properties, that also will be discussed. Now, typically ceramics are defined as a class of inorganic materials or inorganic solids which have covalent or ionic bonding and which are used at high temperature or processed at high temperature, either of the two. Either it can be processed at high temperature or it can be used at high temperature. In both the cases, you can call that class of materials as ceramic materials. Now, here in this view graph, you can see these particular ceramics, let us say X ceramic, has largely ionic bonding. Ionic bonding means like these are cations, positive cations, and these are negative anions. So, positive cations and negative anions, they are ionically bonded to each other, and thereby they form the ionic bonding. The rule of the game is that anions must not touch each other. Anions means this one anion and this one anion should not touch each other. So, therefore, the size of the cation will be such that they will occupy the interspaces between the anions, thereby separating the anions at some physical distance, so that anions should not touch each other. So, you understand what I am saying. So, this is what is that important thing, that anions must not touch each other, and minimum energy anions and cations are as close as possible, so that highest coordination number is possible. Typically anions are larger than that of the cations. The other bonding is this is called covalent bonding, and this is from basic school physics. You know that covalent bonding essentially are formed by sharing of electrons in orbitals of size, and direction is governed by the quantum mechanics. So, this is a classical examples that has been shown here in case of the diamond, and diamonds here the bond angle is 104.28 degree. So, that is the stable diamond structure. Now, several ceramic materials like silicon carbide or silicon, they also have a diamond like structure. Now, coming to the ceramics, like this is something about the bonding of the ceramic, that is the ionic and covalent bonds. One point that I must mention at this point, that none of the ceramics which are used or which are known to the mankind, they do not have 100% covalent or 100% ionic bond. So, that is simply not possible. So, in other words, all the ceramics, they have a mixture of covalent and ionic bonding. So maybe they have 90% ionic bonds and 10% covalent bonds, or vice versa, 90% ionic bonds and 10% covalent bonds. So therefore, the point that you should bear in mind that all the ceramics, they have a mixture of ionic and covalent bonds, and no ceramic that is known to people they have a 100% ionic or 100% covalent bonds. Now coming to that, how the ceramics are typically processed, that is the sintering aspect. So what is meant by sintering? Sintering actually refers to the process of firing on consolidation of powders at T greater than 0.5 Tm. So that is the fundamental definition of ceramics, and at this temperature region T greater than 0.5 Tm, diffusion and mass transport leads to the formation of a dense body. So essentially, if you know the basic material science or basic metallurgy, the diffusion is the process which takes place typically at a temperature region greater than 0.5 Tm, and therefore diffusion and mass transport process takes place extensively in this process, which typically takes place at this high temperature, and that leads to a dense body. So what are the different classification of ceramics? One is the solid state sintering, one is the liquid phase sintering, third one is the viscous phase sintering. Now in this lecture we will be mostly concentrating on this solid state sintering and liquid phase sintering, not the viscous phase sintering. And we will see as we go, we will see that what are the differences between these two classical sintering mechanisms. Now first thing in the sintering process, that you have to make the green body, or you have to make the green compact, and then thereafter you have to do the sintering. So this green compact can be made by either cold isostatic pressing or by simply cold pressing. Now how this cold isostatic pressing they operate? So you have to put the powder inside in a balloon or a particular cavity, and then you have to immerse this powder body in a liquid, and this liquid can be either highly pressurized water or oil, and this liquid once it is put inside this liquid, then from the top you can apply the pressure, and this pressure can be as high as 300 MPa or little higher than 300 MPa. Now according to Pascal's law, when you apply pressure in a liquid medium, that pressure will be uniformly applied to the solid which it is contained in the liquid. So from that basic fundamental principles of applying Pascal's law, what you can immediately realize, this powder material or powder based material, they will experience uniform pressure from all the sides. So therefore this powder body can be made a green body, and this green body we should not have much density gradients because it will have a uniform density throughout the green body. Other things that you have to note here in this slide, that first of all, if this powder need to be mixed with some binder or needs to be mixed with some second phase, then you have to use this planetary ball milling. So you have to put the ball here and the powder here, then you have to close it, you have to put it inside this planetary ball mill, then this mill will rotate at a certain speed, and then by mixing this in the liquid medium, then you get a uniform mixture of A plus B or C plus D, whatever powder mixture you want to get. Now the solid state sintering mechanisms, how do they typically take place in practice? So this slide tells you that there are two spherical powder particle which are coming in contact with each other. Now if the sintering takes place or neck formation takes place, then the center to center distance between these two particles with time is reduced. So what I am trying to say here, if this distance is d1 here and if distance is d2 here, then d2 should be less than d1, and that means they are approaching each other, and that is the way that you can experience that sintering is taking place. Now what happens during the vapor phase transport which takes place in the initial state of sintering, that if you hold that very initial stage of sintering for longer time, now vapor phase transport process cannot encourage that this neck formation and neck growth to the extent like it does when this sintering takes place at the intermediate stage of sintering or final stage of sintering. And in fact, if you hold this powder particle compact at this vapor in the initial stage of sintering, then what will happen? Material transport takes place by the vapor phase, and therefore the grain coarsening will take place or particle coarsening will take place. In other words, this interparticle distance, if it is d3 and initially it is d2, So D3 is greater than D2 in this case. So if the interparticle distance increases, then sintering certainly does not take place and coarsening takes place. Now this mechanism you can clearly see it in this particular view graph, where it shown the 3 particle 1, 2, 3 all are of same size and they are of same shape, spherical shape. Now 3 particles are coming in contact and there is a neck formation in the individual particle. This is one neck, this is second neck, this is third neck, okay. And then once this neck forms, and this is the region in that 3 particle region which needs to be filled by the matter or particles, and this region how they will be filled? By diffusion from this particle, by diffusion from this particle, by diffusion from this particle, okay. And therefore, and this diffusion can take place either by grain boundary region, then it is called grain boundary diffusion, or this diffusion can take place by lattice diffusion. That means when the mass or atom is transported from within the particles to this neck region, then it is called lattice diffusion. In this case you have the lattice diffusion constant which is important. In this case it is the grain boundary diffusion coefficient which is important. Okay, this is like very brief description that how sintering takes place in the 3 particle model. Now rate limiting stage in the solid state sintering is the diffusion of the slowest diffusing ions along its fastest path. Now depending on what temperature you are sintering, if you are sintering at the intermediate temperature, then grain boundary diffusion takes place and then grain boundary is the fastest path. If you are doing at large temperature or highest temperature or the sintering temperature, then lattice diffusion is dominating and then this sintering takes place by lattice diffusion only. So accordingly you can see that what is the diffusion of the slowest diffusing ions along its fastest path. The second one, ambipolar diffusion occurs in case of ionic solids. Ambipolar diffusion means, let us think of aluminium. Aluminium means this is Al plus 3 ions and oxygen ions. So when we are discussing about the sintering of alumina, then you have to find out that how these aluminium ions cations will diffuse and how the oxygen anions will diffuse, okay. So now the way these aluminium ion cations will diffuse, that may be slower compared to the way oxygen ions will diffuse, their diffusion rate may be faster. Accordingly, that the which diffuses faster at a given temperature, that will dominate the diffusion process in the sintering. So you understand. So in case of ionic solids, there are 2 ions, cations and anions. Now depending on whether these cations will move faster or anions will move faster, accordingly you can find out that what is the slowest diffusing ions along its fastest path, and then you can find out that what is the rate limiting stage. So from these considerations, now you know that how you can find out that what is the rate limiting stage in a sintering or diffusion process. Now second one is that surface diffusion, as I said in the last slide, that leads to particle coarsening instead of shrinkage. That is quite straightforward, because surface diffusion means like this surface diffusion actually increases the particle to particle distance, and thereby the surface diffusion process encourages the particle coarsening. Now third one that we have written here, that only lattice diffusion and grain boundary diffusion leads to densification. That means in this stage particle to particle distance, that distance decreases as we increase as the density is increased. Now this slide shows that how this pore shape changes during the sintering process. This is the initial stage. In the initial stage, your 4 particles, they simply touch each other, and the pore shape, this pore shape means that is the interparticle pore shape. This interparticle pore shape has this kind of characteristic shape. Now as the sintering proceeds, that means that mass transport takes place from different neighboring particles to the neck region. Then what will happen? This pore shape continuously or dynamically changes its size and shape. So important thing in sintering is that pores, they changes its size and shape dynamically during the process, and that is what takes place during the process of sintering. Now what happens in the final stage of sintering when most of the pores are closed pores, and this is the grain boundary region. Now grain boundary region, that is one pore that is attached to the grain boundary. So this is, let us say, pore number 1, this is pore number 2, and this is, let us say, pore number 3. Now this pore 2 and pore 3, they are detached from the grain boundary, so that means they are like farther away from the grain boundary, whereas pore 1 is completely attached to the grain boundary. And what exactly has been shown here, now depending on what is the mobility of the grain boundary and what is the mobility of the pore, this will determine whether the pore will be attached to the grain boundary or pore will be detached to the grain boundary. Now from the simple consideration of the lattice diffusion and grain boundary diffusion, from this particular situation you can immediately understand that which pores will be eliminated in the process and which pores will remain. Now you always know that your lattice diffusion coefficient is less than your grain boundary diffusion coefficient, right? Now this particular pore number 1, for that your grain boundary diffusion process is much more active, and if grain boundary diffusion is faster, that means removal of this pore number 1 is much more likely compared to pore number 2 and pore number 3, because these two pores, pore number 2 and pore number 3, for that your lattice diffusion has to take place, and lattice diffusion is always slower compared to your grain boundary diffusion. So from the simple considerations of the diffusional mass transport aspect, you can immediately understand that why the pores which are attached to the grain boundaries, those pores will be removed faster compared to the pores which are away from the grain boundaries. Second point from this slide, or second message from this slide, this is grain number 1, this is grain number 2, this is grain number 3, and this is grain number 4, and you have, this is one pore, this is second pore, this is third pore. So the way these pores are look like, pores appear here in this particular situation. So at the interface of the grain 1 and grain 2, this pore, at the interface of grain 1 and grain 3, this pore, at the interface of grain 2 and grain 4, this pore. So in each case this triple pocket, these pores are formed, and this triple pocket is 1, 2, 4, this triple pocket is 1, 3, 4, and this triple pocket is 2, 3, 4. Okay. Now what will happen during the process of the sintering, since these grains are growing, these grains are growing, and these grains are growing, and the geometry of the grain boundary is such that the grain boundaries are much more mobile. So this grain boundary will move this way, this grain boundary will move this way, and this grain boundary will move this way. Then what will happen? 4 will collapse. So 4 will completely collapse during the process of sintering. And what will be the result? The result is that this is grain 1, this is grain 2, this is grain 3, and 3 pores now will come together, and there will be pore growth process that will take place. Okay. So what is the net result? That grain growth is also accompanied by the pore growth. Initially your pore size here, let us say if it is 2 micron, it is 2 micron, it is 2 micron, then at the end of the sintering process this pore size would be much larger than 2 micron. That is number 1 point. Number 2 point is that initially if your grain size of 1, 2, 3 is 10 micron, that at the end of the grain growth process your 1, 2, 3 both the grains will increase in size. So it will no more be 10 micron. So you understand the physics of the process, that during the sintering your grain growth and pore growth both will occur simultaneously, and that is determined by the your geometry or geometrical curvature of the grain boundaries also. Okay. So this is like, you know, from the very basic sintering theory, how you can explain the fundamentals of the sintering process. Now based on all these considerations, people have plotted the grain size versus pore size, and this is the grain size here, and this is your pore size is plotted along x axis. Now what you see, that this is the case of pure metal, like it's no dopant. Now this region is the region where there is a pore separation that takes place. This region where there is pores will control the boundary motion, and this is the region, this is the grain boundary will control the boundary motion. Now what is meant by pore separation? If you go back to this particular slide here, pore separation means that during the sintering, at certain point some scenario, some situation will come like this, that the pores will be separated from the grain boundaries and they will be isolated pores inside the grains, and you do not like that isolated pores to happen in your sintering process, because you know if the pores become isolated, then what will happen, these pores will be very difficult to be eliminated during the sintering process. So those pores will remain, because your lattice diffusion is always slower compared to your grain boundary diffusion. So from these considerations, it should be very clear to you that you do not want your pore separation to take place during at any point or at any stage during the sintering process. And that is what has been shown here, that you know that during your sintering, that particularly final stage of sintering, your grain growth or grain size also increases, your pore size also increases, okay. But if your grain size increases means you are going these directions, if your pore size increases means you are going this direction, okay. Now if you by chance that you are entering into this region during your sintering process or in this hatched region, then what will happen, all the pores become now separated from your grain boundaries, and then whatever the holding time or whatever the time you hold at the sintering temperature, you cannot remove these pores during your densification, and you will get completely material with much less density than what you have expected otherwise. So this you can expect from your very basics of sintering process. Now what would be the strategy that you should adopt then? The strategy would be, now for example, if you add some impurity is like if you can sinter alumina, or in this alumina you can add, let's say 1% magnesium oxide. Remember, alumina is an important bioceramic because this alumina ball is used as a femoral ball head in the total hip replacement. Now if you want to make alumina ceramic and then if you add this 1% magnesium oxide, then this dotted line essentially indicate that how this entire the boundary of the pore control and grain boundary control, or pore control and boundary control, they are shifted towards the right. And the more importantly, you notice here now that this pore separation also has been shifted towards much up. This region or this region, you are kind of quite safe as far as your sintering process is concerned. So that is therefore that you can choose certain binder content, or you can choose the composition of your ceramic in such a way that your pore separation area that you can avoid during the sintering process. And if you can avoid strategically, then you will end up having ceramic with less and less amount of pores and more density of the material. Okay, this is that one of the classical plot which tells you that how density increases with the temperature. The firing means it is a sintering temperature. Firing and sintering, they are like synonymous words. In the many industries, they always use the firing temperature, they do not use the sintering. Sintering is more scientific terms, firing is more industrial terms. Now what you see in that sintering conditions, the density versus firing temperature. Now if you use the coarse powders, then your density it keeps on increasing, and this does not increase in a very linear fashion, but it still increases beyond a certain density values quite steep manner, and then goes to the 100% theoretical density. If you use the finer powders of the same ceramic, then your curve is shifted towards left, and then you are actually completing the densification little bit earlier than coarser powders. Now if you go to this hot pressing technique, so these two things, this is done in the pressureless sintering, this is also done in the pressureless sintering technique. Now this is your hot pressing route, and in your hot pressing, if you see that how this curve looks like, hot pressing the curve is shifted more towards left hand side, and that means that in the hot pressing route your density increases much more steep, and your hot pressing does not require much longer time period like the way it requires for the pressureless sintering case. So therefore in the hot pressing you can quickly densify or you can quickly sinter these materials at a much faster rate, because here densification takes place much faster. The other thing that you notice from this curve is that entire sintering can be classically divided into 3 stages. One is the initial stage, the second one is the intermediate stage, and the third one is the final stage. So initial stage of sintering means it is just like the neck formation takes place. Okay, the particles, they come in contact with each other, interparticle distance starts decreasing with increasing time. Intermediate stage of sintering means your grain boundary diffusion process started, and intermediate stage of sintering, your pores become, they form like a continuous channel, it's more like a cylindrical channel of pores that forms. And in the final stage of sintering, your pores become isolated, and that is the period that you are holding it for longer time, so that you are allowing lattice diffusion to take place, and therefore you are essentially trying to remove this closed porosity from the material. Now this is the grain growth which takes place in the ceramics. One is the called normal or continuous grain growth, one is called abnormal or discontinuous grain growth. Now what is normal grain growth? Normal grain growth means, suppose your grain size distribution at any given time T1 is like this, your grain size distribution changes with at time T2, where T2 greater than T1, and then it is simply shifted along the x-axis to a new distribution value. What it means? That it means that your mean grain size increases with time, but the overall shape of the grain size distribution remains same. So it is called normal grain growth, right? Abnormal grain growth means initially your grain size is like this at time T1, at time T2 your grain size also is giving you two type of distribution, and that is called unimodal distribution to bimodal distribution. You have one mode here and you have one mode here. What it means? This means the average grain size not only increases with time, but also there are few number of grains which is much more coarser size that appears as you sinter it for longer time period. So that is the definition of the bimodal grain growth. The question is that why this grain they grow with time, and what was the reason for this? The reason is very simple, and that is again comes from the basic geometry. Now if you look at this slide, you will realize immediately that the grains which has a grain edges more than 6 grain edges, they will grow at the expense of the smaller grains. So here you can see there are few grains which has 1, 2, 3, 4, 5. This is the grain 1, 2, 3, 4, 5. So this has the grains which has a grain edges 5. This is the grain which has a grain edge 6. That means these grains with 6 grain edge, they are equiax grains without any curvature. Without any curvature means the grain edges like straight. They do not have any curvature in the grain boundary. Now if the grain edge is more than 6, like here for example 10, like this is one grain edge, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this case your grain growth will take place, because your grain boundary now is much more curved, and from basic geometry it needs to be curved. It cannot be simple straight line, because with the grain edge of 10 your grain boundaries also will be curved. And what you see here in both these cases and both these cases, the grain boundary will be now dragging towards diagonally this way and this way, so that these grains will now grow. Now entire volume will remain constant, so this grain growth can take place only when whatever smaller grains it has in the neighborhood, that will be consumed. Okay, it is just like in a society where rich people live and poor people live. So rich people's property will only increase at the expense of the poor people. So similarly, the grains which have a grain number is more than 6, they will grow at the expense of consuming the smaller sized grains which has a grain edge of less than 6. Now typically the sintering process, they can be classified again from the technological point of view. One is called pressureless sintering. Pressureless sintering means you are sintering without any pressure, and another one is a hot pressing technique. Hot pressing means, as the name suggests, you press it when it is hot. And how this process takes place in practice, you have these ceramic powders here, which you fill this mold here, graphite mold, and in this, from this graphite mold, from the bottom and top, okay, you start pressurizing, and from this resistance heating here, you are actually also heating it from externally. So the ceramic powders will keep on experiencing more and more temperature, and you push the pressure when the ceramics is reaching at high temperature. As a result, what will happen? There will be shrinkage from both these directions, and this entire powder compact is contained in this graphite die punch assembly. So sidewards there is limitation, or there is restriction, and the temperature in the hot pressing can go very high, as high as 1800 to 2000 degrees Celsius, and this is how the hot pressing takes place in practice. However, the basic thing in the hot pressing is that you can only make very simple shaped materials, not very complex shape. Now, what is the mechanism of hot pressing? Mechanism of hot pressing means you have these 4 particles model. So 4 particles, they are coming in contact with each other and they are touching each other, and then you are applying pressures from both the ends, okay, and this is your graphite die wall. So this way there is no expansion possible. That means there is a lateral constraint here, this constraint and that constraint, and then these particles, now they have the only way that this shrinkage can take place if this center to center distance keeps on decreasing, okay, and that means this particle boundary should become more and more flat, and that leads to the material which has a equiax type of grains. Equiax means that is n is equal to 6, as I have explained few slides back, okay. Now how these grains form, now you can understand that this edge must be, this is a part of this one particle, this edge must be part of the another particle, but due to the external pressure application and due to the fact that only longitudinal displacement is possible, not the transverse way, that this particle distance becomes more flat, and that is how this entire grain structure, they evolve more like a equiax type of grain morphology. Now coming to the liquid phase sintering. Liquid phase sintering means the way this sintering takes place in the presence of the liquid phase, and this liquid phase, the name suggests that you form some liquid during the sintering process, and then you, in the presence of the liquid, your shrinkage takes place. So again, here is grain number 1 and this is grain number 2, and this is your liquid phase here, this is your liquid phase there. So this is your liquid, okay. Now this liquid, in the presence of this liquid, it has some surface tension and surface energy. This is, let's say, gamma SL, this is also gamma SL. So this way it is gamma SL, this way is gamma SL, and this way it is gamma GB, okay. And if you know this angle theta, the entire angle theta, then this half of the angle would be theta by 2. So from the basic physics, then you can find out that gamma GB should be equal to 2 gamma SL cos theta by 2, okay. That comes from your basic equilibrium, and from that you can find out theta value if you know the gamma GB and gamma SL value, right. Now similarly, there is also another angle here, and here again you have gamma SV, that is solid vapor interface, you have gamma LV, that is liquid vapor interface, and this is your gamma SL, that is solid liquid interface. Now from your basic geometry, again you can find out the relationship between the 3 interfacial energies, and both the contact angle at the solid liquid vapor interface are wetting and solid liquid, they actually determine whether this liquid phase is will wet the solid particles or not. So even if you have the liquid phase, if it does not wet the solid particles, it will not serve the purpose of liquid phase sintering. Only in places when it will wet. Wet means this liquid phase has to flow in between this grain boundary region, and once it flows, then this has to dissolve in this liquid phase, this has to dissolve in this liquid phase, and thereby the diffusional mass transport process will take place faster, and accordingly you can get more and more diffusional mass transport and faster diffusion, and that will actually increase that shrinkage. Now what happens in case of the liquid phase sintering? There are 3 mechanisms, and these are like 3 overlapping stages. That means you cannot essentially say that this will take place first, this will take place second, this will take place third. That means overlapping means this and this can overlap, this and this can overlap. The first stage is that rearrangement of the particles. So this is your liquid, entire stage is liquid, that liquid has formed. Now in the powder compact you have some smaller particles and you have some bigger particles also. Now what will happen, the smaller particles will dissolve here in this liquid phase and then they will go and reprecipitate on the coarser solid particles, and then as a result these coarser particles will actually increase in size. So that means there will be grain growth of these coarser particles at the expense of the smaller particles. That is what exactly happens during the grain growth of the solid state sintered particles. If you go back here also I have shown you that coarser particles will grow at the expense of the smaller particles. Here also in the liquid phase sintered materials I am showing you again that you have these coarser particles and you have these smaller particles, and the smaller particles will dissolve in the liquid phase and then thereby they will reprecipitate on the solid particle surface, and the solid particle now will grow and this grain growth will take place at the expense of the finer particles. So liquid phase sintering essentially takes place by three overlapping stages. The first one is the rearrangement of particles. Rearrangement of particles means that once the liquid phase forms at the interparticle regions, then all the smaller particles and coarser particles they rearrange themselves. So that means they can float and they can rearrange themselves, and that occurs within around 10 minutes of the formation of low viscosity sintering liquid. Remember that sintering liquid, what it forms at the interparticle region, it should have a low viscosity. If it is a high viscosity or if it is a very highly viscous liquid, then what will happen? The diffusion process will be much sluggish. You just think, you think of water and you think of some polymeric gel or something. Now in the water anything can diffuse faster because it is a low viscosity liquid, but in a polymeric gel which is a very thick and viscous, then that mass transport or diffusion or mass transport will be much more sluggish. So one of the thing in the liquid phase sintering, that your sintering liquid must have a low viscosity, okay, otherwise this diffusion or mass transport, that entire purpose of having the sintering liquid will not be fulfilled or will not be served. Now that is driven by the attractive capillary pressure formed due to the lower contact angle, that is less than 60 degree. This lower contact angle means we are talking about this angle or this angle which is less than 60 degree. So there is some requirement of the geometric angle, and this geometric angle that takes place solid, liquid, vapor, that is less than 60 degree. Now what happens to this contact angle, that is at the solid and liquid? Now if you go back to the slide, it says that the solid liquid interface angle should be less than 50 degree. So roughly in both these angles should be around less than 60 degree. So this one specifically around less than 60 degree, this one less than 50 degree. And if this angle or this geometric criteria is fulfilled, then that essentially this combination of parameters will influence the liquid phase sintering to take place more effectively. The third one is that once this liquid phase becomes very smaller in volume fraction, then solid state sintering and microstructural coarsening occurs, and that typically takes place at the last stage of sintering. Now this is an example of the liquid phase sintered materials, although it is not a bioceramic zinc oxide, but it is a varistor applications, but zinc oxide also can be added as a second phase in this hydroxyapatite to improve the antimicrobial property. This is grain 1, this is grain 2, this is grain 3. In this grain 1 to grain 2, grain 3, these triple pockets, this is the phase where liquid phase is formed, and after sintering this liquid phase actually remained there as a residue, and that is the evidence that liquid phase sintering has taken place and lead to the densification of the zinc oxide material. Okay. Now this is like some other examples of the ceramics, basically structural ceramics. Now what you see here, that liquid phase which is formed in the TiB2 and molybdenite. So this is the triple pocket where the liquid phase forms, and this liquid phase has completely different composition compared to these two TiB2 and molybdenite phase. Another examples of the liquid phase in the silicon nitride or another ceramic materials, where you can see this liquid phase has formed at the triple pocket, that is the glass phase. This is one liquid phase, this is another liquid phase. In this transmission reactor microscope pictures, you can clearly see that there are several places the liquid phase that has formed, okay, and this leads to the good liquid phase sintering property of this silicon nitride based materials. Now this is like very high resolution TEM, that is high resolution transmission reactor micrograph, and what you see that this is part of grain 1, this is part of grain 2. In the grain 1, your atoms are aligned in this particular region. In grain 2, your atoms are aligned in this particular region, okay. So therefore there is a orientation difference, and this is the region where is disordered region, and in this disordered region your liquid phase has formed, and this is the amorphous or glassy phase has formed because you don't see any crystallinity in this phase, and that is again the evidence that liquid phase sintered materials that formed over a very narrow range 1 to 3 nanometer thickness. Now I will give you some examples from the bioceramic materials. Now how these solid state sintered and liquid phase sintered materials they look like, or how do their microstructure they look like in these bioceramic materials. Now it is the examples from pure hydroxyapatite. Now pure hydroxyapatite they have very good biocompatibility property. If you sinter them at 1000 degrees Celsius to 1400 degrees Celsius, what you see that grain size they increase. At 1200 degrees Celsius, it further increases to 1300 degrees Celsius, and also it further increases to 1400 degrees Celsius. At 1400, you can see really fairly coarse grain structure in the materials, and this coarse grain structure essentially indicates that you have large number of coarse grains and very few number of fine grains. So therefore it will have a bimodal grain size distribution, okay. So number of coarse grains and there are number of solid few small grains. Such bimodal grain size distribution is not that evident in this particular microstructure. However, here there are some bimodal grains are formed. Interesting things that you observe here, that in this bimodal, these coarse grains they have some kind of porosity, and which are really coarse pores which are present inside the grains. So this actually shows that although it is more than 99% theoretical density, there are still some pores which are left to be sintered or tend to be closed. One of the material that has been recently attracted attention is the BCP. BCP is the biphasic calcium phosphate materials, and biphasic calcium phosphate means it has a mixture of tricalcium phosphate as well as the hydroxyapatite. And tricalcium phosphate and hydroxyapatite, this mixture when they sintered, after the sintering, what you can see, it leads to a very coarse porosity. Now if you look at the microstructure, this is 100 micron, so there may be a 300 micron or this may be a 200 micron pores. These are commonly observed in this biphasic calcium phosphate materials. Also it has a microporosity in this biphasic calcium phosphate ceramics which are sintered at 1050 degrees Celsius, and this microporous materials, it is a consequence of temperature and duration of sintering. So higher the temperature, lower is the microporosity. That is very evident from your basics of sintering. What you observe here, this is 1 micron size, and sometimes these pores they may not be interconnected and they may not be very coarse, and the size of the pores is somewhere between 1 micron to 5 micron, around that range, okay. And there most of the cases the two neighboring grains they are joined together at various places. This is more clear picture of the microporous BCP ceramics which are sintered at even 1200 degrees Celsius. So volume fraction of the porosity in this particular case should be less than when it is sintered at 1050 degrees Celsius, and here you can see that these are the porosity, and there is a long channel of pores here, and these are the porosity here, and they are different places. Okay, coming to the mechanical behavior of brittle materials like ceramics. First I will show you that how you can measure the stress intensity factor or fracture toughness of the ceramic materials. What are the different crack systems and different modes of loading in these materials, and why the strength is variable in nature in case of ceramics, and how to measure strength of ceramics, and what are the different concepts of toughening mechanisms. Now first let us understand what is meant by ductile fracture and what is meant by brittle fracture. Ductile fracture means that prior to the fracture material undergoes extensive deformation, and that has been shown here, and it is typically cup and cone type of fracture. Brittle fracture means that the material is fractured to completely two surfaces without much deformation prior to the fracture. Now this brittle fracture takes place in a very unpredictable brittle manner. Now what is the difference between fracture and plastic flow? Now you have this atomic plane here. Now because of the crack propagation, crack is nothing but the region of the microstructure which is essentially formed by the breakage of the interatomic bonds. So this is the interatomic bonds here, this is the interatomic bonds here, and in both the cases interatomic bonds are broken. Now if these cracks will propagate further, then subsequently all the interatomic bonds will be broken, and then entire material will be simply made into two halves. This is part 1 and this will be part 2, and that is taking place under the action of the tensile force. Now this is called the fracture. Now what will happen when there will be plastic flow of the materials? Plastic flow means you have a dislocation in the structure, and these dislocations are present in varying number. Now when you apply the shear stress tau, here is tau shear stress, then subsequently all the interatomic bonds are sheared, they are broken and remade, they are broken and remade. So essentially the dislocation motion will take place. And why metals are tough? Metals are tough because ahead of the crack tip, in this region you have the material that yields and that plastically deforms, and this region is actually the dislocation motion which takes place. Okay, this is the yielded region. Now another reason that why fracture takes place in brittle solids more easily than the fracture takes place in metals. Now in the brittle solids, let's take an example of the rectangular block which has a edge crack, and in this edge crack region, ahead of the edge crack, you have the region where the material, any volume element, let's say this is a volume element, this volume element will experience the stress which is sigma c, and this sigma c stress will be much larger than you are actually applying externally, which is a nominal stress sigma. Then how larger it can be, how it can be mathematically described? The sigma c would be 1 plus 2 square root c by rho into sigma. What it means? This means that it can be approximated as 2 square root c by rho multiplied by sigma. So what is c? C is the half crack length here, and what is rho? Rho is the radius of curvature. Okay. Now you think of the situation, if a crack they look like this, and if c is larger, that means this length increases and rho is smaller. Rho smaller means it is sharper and sharper crack. Okay, and if it is a sharper and sharper crack, then rho is less means sigma c will increase, because sigma c will increase if rho decreases, okay, or c increases. Okay, so as I am showing you the example, that if you consider this is a crack face, now if crack length increases, that means c increases. C increases means sigma c will increase, and if cracks become sharper, that means radius of curvature also decreases, and also then the sigma c will increase. So essentially what you see here, that within so you don't need to change the external stress at a given stress when sigma is constant. By changing the length of the crack or by reducing the radius of curvature of the crack, you can experience more amount of stress at this particular localized area. Now if this stress is much larger than the interatomic bond strength, then what will happen? Then bonds will be ruptured, and if the bonds are ruptured or bonds are broken, then these cracks will completely go through the material, leading to the fracture of the two surfaces, and this is 1 and this is 2. So that is how this brittle fracture that takes place in the materials like ceramics. Now the question is, this kind of things also happens in metals, that why metals they do not fracture so easily like ceramics? Answer is that at this growing crack tip area there is dislocation motion, and that dislocation motion leads to the yielding of the material. Yielding means, that means material will be plastically deforming, but in ceramic that plastic deformation is not possible, and as a result ceramics can be easily fractured into two pieces by simply the crack propagation. Now from these examples, previous examples, it must be clear to you, it is not the external stress alone which will be responsible solely for the fracture of the material. It is the external stress coupled with the crack length, both will contribute to the fracture of the ceramic materials. Therefore, a parameter which is known as K1C, that is the critical stress intensity factor under mode 1 loading, has been defined, and this definition is as follows: K1C is equal to Y sigma F square root pi A. And what is A? A is the half crack length. If the cracks are present within the volume of the material or inside the material, then A is the half crack length. Now, if the cracks which are present at the surface, then it is called, then you have to take the full value of the crack. So, for surface crack, the A is the full crack length. If it is the within the volume of the material, then A is the half of the total crack length. Now, if it is pulled in tension, then what will happen? K1C actually increases, and this K1C is a material property. So, once this K1C is fixed, that means it is like that. If your strength is fixed, and strength is nothing but maximum load divided by the cross sectional area. Now, if your strength is fixed, your cross sectional area of the specimen is fixed, then you can find out what is the maximum load the material can bear without fracture. Similarly, if you come to the description of the fracture toughness, if your fracture toughness value is fixed, let us say 10 MPa square root meter, and if I tell you this material has a fracture strength of certain MPa, let us say 100 or 200 MPa, then you can immediately find out what is the minimum crack length or what is the maximum crack length that this material can tolerate without going to fracture, okay, from this particular expression. Now, the question is that what does Y signify? Now, Y is a constant which depends on the mode of loading, like how you are loading, whether it is a uniaxial tension, whether it is a biaxial tension, and so on. At the same time, Y depends on what is the orientation of the crack, whether the crack is oriented at an angle to the loading axis, whether the crack is oriented transverse to the loading axis, all those things that will contribute to the value of Y. Now, as I said, that K1C essentially means that is the critical stress intensity factor under mode 1 loading, then there should be mode 2 and mode 3. Now, the question is that how these three different modes, they are characterized by that fact. Now, this particular slide tells you that there are mode 1 loading means that is a typical pure tensile mode opening. So, this is the crack and it is pulled in tension. Now, cracks will grow fast and that leads to fracture. Mode 2 loading means it is a shear type of loading. Mode 3 loading means it is a tearing type of loading. Okay. So, mode 1, mode 2, mode 3, most dangerous mode is mode 1. Therefore, K1 is greater than K2 greater than K3. What I am saying is that stress intensity factor under mode 1 is always greater than mode 2 stress intensity factor or mode 3 stress intensity factor. Therefore, if you want to really understand that what is the maximum fracture toughness that a material can have, then you can find out that only mode 1 loading, and that is why people always are interested to find out that what is mode 1 loading. Now, question is that why ceramics are brittle? Now, ceramics have ionic bonding, as I have said that ceramics have ionic bonding and covalent bonding. Now, ionic bonding means that dislocation movement only can take place on certain specific angles, because you have the positive ion cation, you have the negative anion, you have positive ion cation, you have the negative anion. Okay. Now, one anion will be placed at the just below the positive ion and one cation will be placed just below the negative ion. Now, if you simply stress them, apply the shear stress, what will happen? The second row, this anion will be displaced by one movement, then what will happen? This anion will be just below the second anion, and that is not possible because two anions cannot touch each other. You understand what I am saying? So, therefore, this kind of dislocation movement simply is not possible in the ionic solids. But how this ionic solids can then dislocation will move? If the dislocation can move at a plane at an angle 45 degree to the stress axis, then that dislocation movement is possible, because then this positive cation will displace another positive cation and this will displace another positive cation. So, the total neighborhood in this ionic arrangement will not change. So from the consideration of the basic ionic arrangement, you can immediately notice that dislocation movement is not easy in ionic solids. So that is number one. Number two is that covalent bonding, and in this covalent bonding what will happen, that these two bonds, let us say it is a carbon bond, and two carbon bonds are directionally they have a very directional type of bonds, and you require really large amount of energy to break this directional bonding, and therefore the ceramics, they have a much, they are really strong and they don't have this good fracture toughness. Third one is that dislocation core width in ceramics are much more narrower than the solids, and dislocation core width means how it is related to tau Pn. Tau Pn is the Peale's number of force, and it is related to some exponential minus 2 pi w by b, where w is the core width and b is the Burgess vector. Now if it is proportional to the exponential minus 2 pi w by b, and if the core width is small, then what will happen, since it is exponential minus, so that will increase. Okay, so the tau Pn value will increase, and then if the tau Pn value will increase, that means you have to really apply large Peale's number of stress to move the dislocations in the ceramics, and that's why ceramics are also brittle. Fourth point is that you have less than 5 independent and active slip systems. Slip system means it is a combination of slip direction and slip plane. Now if any material which has a less than 5 independent slip systems, then that material as per the von Mises criteria, they are not ductile at all, and that is the result that for a given ceramic grain it is very difficult to change its shape by rotation, and that is leads to the strain incompatibilities leading to fracture of the material. How does the ceramic behave in compression? Now compression means you are actually pushing the ceramics from two ends. So tension, you have a very small fracture strength, so it is straight to fracture. That's why it is called linear elasticity or linear elastic solid, because ceramics, they do not have any non-linear elasticity. In case of compression, it has a much larger strength, and this strength is 8 times than the strength in tension. And this compression, if you notice that each time the ceramics break during compression, you will be reflected in kind of some jerks in the compression stress strain curve, and that is what is explained here. Now if there are multiple cracks in the ceramics, because it is a brittle material, when you are pushing compressive forces from two ends, these cracks will increase in size, right? And at certain point, these cracks will lead to the spalling of the material from both the ends, leading to the fracture. Now each time this spalling occurs, that leads to certain jerk in this compressive curve. After some time, what will happen, that at certain point of time, this amount of the material that will remain to bear this stress, that will be very less, and entire material will be shattered into pieces, and that is reflected in this compressive stress strain behavior of this material. This is what I have been telling you, that ceramics, they can only the dislocation can only take place at the 45-degree angle, not in other angles. And this shows that covalent bonding, in case of covalent bonding, if you have dislocations, now each time the dislocation has to move on the application of the shear stress, these bonds has to be broken and they has to be remade. And this bond breaking and remaking, it's not very easy in case of ceramics, and that is why covalent ceramics also are very weak in tension. Now how you can measure the strength in ceramics? Now strength, traditionally for metals you can measure it by tensile force. Okay. Now tensile specimen for ceramics is very difficult to make. So what you do, you can make the flexure specimen, and you can put 2 rolls on the flexure. You can place the samples, and these samples you can break it by pushing it from one end. And when you make this tension sample, you put it on the 2 support rolls. From the top roll you can place a force P, and according to the equilibrium of forces, these 2 support rolls will carry the load P by 2, P by 2. And then this is your tensile phase, and this is your compression phase, and then fracture will take place from the tensile phase, and then cracks will be propagating from the tensile phase to the compression phase, leading to the fracture of the material. Now that how this 3-point flexural strength that can be measured? Now 3-point flexural strength that is measured by 3 times multiplied by force multiplied by span length, and these are the two B and D are the width and the thickness directions. So essentially what you mean by that this roll is that this distance between two support roll is called span length, that is L. You put a top roll and you put a force it by P. Now this length is your L by 2 and this length also is your L by 2. Okay. So the top roll is placed exactly at the center of the span length, and then your other things is that this is your height H and you have the other dimension, right, in this rectangular cross section sample. So that dimension is your B. So you have the width, you have the height, you have the span length, everything has been there in this strength value. So you measure that what is the load at which the fracture takes place, and then you know the geometry of the sample. From that you can calculate immediately what is the flexural strength. Flexure means bending. So this strength essentially measures that what is the maximum strength that a ceramic can carry, what is the maximum stress ceramic can carry without failure under bending. And bending is one of the mechanisms for the bone fracture also. So whenever you put the ceramic material, it is important that you determine that what is the strength in bending. Now I have spent quite some time on describing the sintering mechanisms and trying to tell you that why porosity needs to be removed by adopting a particular sintering mechanism. Now the reason why the porosity removal is important, you can realize now from these particular two graphs, that is how the strength, flexural strength will decrease with increasing the porosity. So as you increase the porosity in these directions, your flexural strength also goes down systematically. Similarly, your modulus of elasticity also goes down systematically as you increase the porosity. So if you have a porous ceramic, that will have a much lower elastic modulus, much lower strength value. That is the reason you remember cortical bone and cancellous bone. Cortical bone is a much more compact shape, less porosity, so it has a much better strength, much better elastic modulus. Cancellous bone is a much porous material, much spongy bone, so that's why you have a poor elastic modulus and poor strength values. Okay. So for a given ceramic material, whenever you are talking about macroporous ceramic, microporous ceramic, the thing that you need to bear in mind that in this kind of porous ceramics, your strength and elastic modulus will be very low. Okay. So I think I'll stop here. In the next class, I'll teach more about the ceramics mechanical properties.